Using real images of galaxies from astronomical surveys of our universe, a neural network can be trained to classify these with impressive accuracy. This visualization shows the output of the penultimate layer of the deep neural network during training, as it is learning to classify two types of galaxies, spirals and ellipticals. The network output can be embedded onto 3D coordinates for each image. Visualizing these coordinates, we can see how the network discovers two distinct clusters of features for each galaxy class. Large astronomical surveys take images of just a fraction of the roughly 100 billion galaxies that are scattered throughout the observable universe. Looking at telescope images of distant galaxies, researchers can understand how they formed by classifying them according to their shapes. We can see galaxies which look like rotating disks with spiral arms, which we call spiral galaxies, shown here in blue, or galaxies which look like large spheres of stars, which we call ellipticals, shown here in yellow. An artificial intelligence algorithm, called a neural network, can be trained to recognize these two distinct classes of galaxies using these images alone. The neural network has millions of free parameters, called weights, which are arranged in layers and are tuned as we train the network. As the weights in the neural network are trained, we can visualize their response at each stage or epoch in the training process. Here we are visualizing the output from the penultimate layer in the network. These two images of a spiral and elliptical galaxy elicit similar responses from the network in the beginning, as it has not learned to distinguish them. As training progresses, we unfreeze layers in the network, allowing their weights to be adjusted and learn distinct features in the images. We can see that unfreezing layers during the 5th to 10th epoch causes a large response from the network to the spiral galaxy image. These newly activated layers are important for allowing the network to learn certain features. Let us see the network being trained again on these two images and overlay the outputs to highlight the differences at different stages. Expanding out the final layer in the network when it is fully trained, we can clearly see the difference between the network's response to the spiral and elliptical galaxies. The penultimate layer of weights after training are a little over 1,000 parameters, which we can represent in three-dimensional space using a projection algorithm. The projection algorithm essentially condenses the relevant information which the network has learned and allows us to visualize its representation of the spiral and elliptical galaxies. Let us view the training of the network again for all of these galaxy images. Spiral galaxies are shown in blue and elliptical galaxies in yellow. In the beginning, before the network has been trained, most of the galaxies are misclassified, as shown here in red. This time we will show the condensed 3D representation for each of the images as the network learns to classify them correctly. As training progresses, the number of misclassified red images is reduced at each iteration. This is the final 3D representation of what the network has learned for a sample catalogue of over 1,000 galaxies. The spiral and elliptical galaxies form two very distinct clusters of yellow and blue points, with no overlap. Looking again at the actual galaxy images, we find that the network has correctly separated these two classes. Overall, this novel method allows researchers to achieve state-of-the-art accuracy classifying astrophysical objects in our universe, which will ultimately allow us to understand their evolution.